So first of all, let me thank the organizers for the invitation, and I was and I'm still really looking forward to this workshop and to all the discussions. So thanks. And after the thanks, an apology for those of you who have already heard some or many of the things I'm going to talk about. But since for some inexplicable reason, this is not textbook material. So I have to repeat it often to people that have it as entirely new. So, and before I start with the actual content, a bit of preliminaries. For the sake of the talk, I will just mention and use words from philosophy in a very naive way. So let me just clarify a bit how I will use the terms and what is the sort of perspective I'm taking here. Anything which will have to do with the existence or being fundamental, not fundamental, and all of that, so with metaphysics, will be simply inferred from physics with no further argument or justification. I will speak of things that are there, or the world, or things like this, adopting a sort of entirely naive realism, which I'm aware is naive, and I use it only from a methodological point of view. It just simplifies my life and could be heuristically useful. I don't share much of that perspective. In fact, if I really have to put on the table what I'm sympathetic to from that point of view, would be some sort of participatory realism, call it as you prefer. And I try to say something there, but it's not really crucial. It will be a bit more relevant towards the end of the talk. I distinguish existence and fundamentality. So I would say that something exists. I would argue that something exists simply because it features crucially in some corner of our best models of the world. Even if it does not feature among the basic or assumed elements fundamental of the same best models of the world. So the whole point of the talk, and I guess of the workshop, is the possibility that the key elements in our best theories of quantum gravity are not spatio-temporal. So in this sense, space and time are not fundamental, but emergent. So they exist, but they're not fundamental. And I will assume the notion of emergence as a binary-oriented theoretical relation characterized by robustness and novelty, and involving necessarily a lot of approximations that I learned from Butterfield. And I think is the more or less customary way in which physicists think about and use the word emergence. So if I want to discuss how space-time emerges and what that implies, maybe I should first clarify what I mean by space-time. So what is to emerge? Many aspects one can refer as properties or features or characterizing elements of our notions of time and space. Localization, so the notions of event, something that can be localized somehow in space and time. Contiguity, which has to do, of course, with the topology. The dimension, the extension, so duration in time, length, so all notions of geometry. And the other set of properties have to do also with the causality, so the signature, the distinction between time and space, and the ordering of events. So possibly all of this, or many of these aspects will have to be recovered in some approximation by more fundamental theoretical structures. In fact, they're not, of course, independent. What we mean by time and space normally is a combination of all of those aspects. And in fact, causality, as we understand it, is a combination of all of those aspects. So this is not a list where you can just remove one element freely because they're all independent. So I adopt the natural list position that I mentioned at the beginning. So our best theory of space-time as we know it is generativity. So what is space-time according to generativity? First of all, is a physical system. We have a theory that tells us about its properties and defining and equations and so on. So this is textbook material. And because we all went to primary school, I assume everybody knows about generativity. So we have a model of the world in which we have some four-dimensional smooth manifold and a metric field with Lorentzian character, so Minkowskian signature. We identify gravity with space-time geometry. So the notion of the ability to compute distances, curvature, volumes, all of that, and the causal structure. And this is the physical system the theory is about. It has its own equations of motion, it interacts with the other fields, and so on. I'll take this description of space-time as granted. This is basically what I mean by space-time. This is this sort of stuff that has to emerge from something else. Then I want to distinguish two notions because sometimes we conflate them and it's very dangerous. Very often we speak of emergent gravity. In that context, we identify gravity to be space-time curvature, or we identify gravity with the dynamical aspects of space-time. And those would be emergent in an emergent gravity context. It could be perturbative or non-perturbative, but space-time, usually a Minkowski flat space-time, is assumed to be fundamental. One starts from something like that, and gravity in the sense of curved space-time or dynamical space-time emerges. And examples many, and perturbative quantum gravity is a bit of that type, but analog gravity would be another one that is very inspiring, but the type of space-time emergence we have there is in fact just emergent gravity. Emergent spacetime would be more radical because it would mean that one or more of the basic spacetime structures that I listed earlier are emergent, not fundamental. In that context, gravity is emergent necessarily. So it's the second includes the first. And in particular means that flat spacetime is itself an emergent construction, emergent structure. So if you are pondering about this second possibility, the next questions would be, okay, what sort of new degrees of freedom space-time emerges from? Are there some sort of discrete structures? Is it a purely algebraic data you're assuming as fundamental? What sort of dynamics can you assign to these new degrees of freedom? I said that I take for granted the view for which space-time is a manifold and a metric. And then you have fields defined on the manifold that somehow concur to the properties and to the dynamics of space-time. This is the naive view. In the classical theory, why naive? Because we have diffeomorphism invariance in GR. And it will be relevant for all the pain we have to suffer later on for the emergence of space-time. So let me expand a little bit on this. A diffeom maps from one point to the manifold to another. It carries the fields along, but basically maps a field at a given point in a manifold to a different field at a different point in a manifold. If you have a theory defined by some equations of motion for dynamical fields that they collectively call phi, with some background structure, sigma, you will say that the theory is generally covariant under diffuse, a subgroup or the whole diffuse group, if the equations are satisfied, if and only if the mapped equations are satisfied. So you transform all the fields and all the background structures by a diffuse. If that is true, then the theory is generally covariant. Well, if that is true for a subgroup of diffuse, the theory is covariant under that group. Otherwise, it's generally covariant. This is an entirely trivial statement. If you're defining your theory in terms of geometric structures, fields, tensors, vectors, all that stuff, and you're not writing it in the wrong way, in a specific coordinate frame or something like that, it's just a matter of language, this is going to be satisfied. There's no content in this, it's just language. The theory is invariant under diffuse, a subgroup of all of it, if the equations are satisfied, if and only if the equations in which we only map the fields for given background structures are still satisfied. So you're mapping different solutions to the same equations. Or, of course, assuming that you've written everything in a clever way, so in a generally covariant language, if and only if the equations for the same fields, but with the mapped background structures, are satisfied. So you have full diffeomorphism invariance only if, in your theory, either you only have invariant background structures, or, of course, you have no background structure at all. It is in this sense that diffeomorphism invariance is equivalent to background independence. Why is this relevant for our story about space-time? Because it shows that the previous view, now I'm going to click something, may do something wrong. No, okay. This view of what space-time is, a manifold and the metric, is naive. The manifold, the points, directions, atlases, and so on are unphysical. They're not invariant under the symmetries of GR. So space-time cannot be associated, cannot be identified with the manifold with the additional metric structure. The events are not the manifold points. Time is not a time-like direction on the manifold, and so for space. It means that the field themselves, with the values depending on the different points on the manifold, are not physical objects themselves. So GR is usually formulated, and we usually use so we do it all the time, and it's all good. I mean, provided we keep in mind what we're doing, is formulated and used in a highly redundant language. Why is this relevant for emergence? Well, if your goal is to have the whole GR structure written in this redundant language emerging from something else, you may be asking at the same time too much and too little. Too much because you're trying to reconstruct from something presumably more fundamental and directly physical in some sense, a lot of redundancy. At the same time, maybe you're asking too little, because I don't care that you can recover all the redundant stuff. Show me that you can recover the invariant physical observable quantities from some more fundamental structure. Okay, the relational strategy in classical and then quantum gravity is the only way I know. There may be others, but it's the only one I know. Through which you can define and then compute, possibly, it's very difficult, local space-time quantities. So give a meaning to what you mean by local physics. And the idea is that you have to introduce and use reference frames, physical frames, so some subset of degrees of freedom dynamical degrees of freedom in your theory, use them to define a frame which defines what it means to be localized in time and space. It's a definition of time and space for the other dynamical degrees of freedom. Is what we do all the time, except that we normally work with this in the idealized limit in which a physical frame behaves like a coordinate frame. And so we say you take GI, you write it in a set of coordinates, it corresponds to an observer that does that and that. Yes, in the limit in which the observer has no back reaction on the other fields, no back reaction on the geometry, has no quantum property and all of that, then it behaves like a coordinate frame. And then it's a gauge, it's a particular gauge in GR. An example very stupid would be you have a Ricci scalar that is a function of the metric at a point. You have 4 scalar fields at a point. You invert the point or the coordinates for the point for the 4 scalar fields. You plug it back in the Ricci scalar, and then you have the Ricci scalar function of the metric defined at the location identified physically by the 4 scalars, 4 scalar fields. That quantity is a different variant one, relational. We do not know a formulation of GR realistic, and I can discuss why the ones we know are not fully realistic, purely in terms of such different variant quantities. At the quantum level is worse, because the 4 scalar fields, not only the metric, but the 4 scalar fields will have to be quantum. So try to do that procedure with quantum clock and rods. So the general point that one should learn is that physics, ultimately, we're doing foundations of physics, right? So it's not just you want to do the calculations, it's a bit more. Ultimately is on superspace, and superspace has nothing to do with supersymmetry in the old Wheeler tradition. Superspace is just the space of field configurations, including the metric. So physics is on that space, not on the manifold supporting the fields in the redundant way of writing our theories. Okay, so space-time cannot be just identified with the manifold or with the metric on the manifold and so on. That at best is an approximation. So we should not expect to find the manifold at the fundamental quantum gravity level. Our fundamental theories may be defined in such a way that manifold never appears. Therefore, we should not expect them to recover a manifold at some effective level unless we decide to reintroduce it because it's useful to have that type of redundancy, which is fine. I'm fine with, I'm a methodological anarchist, so do whatever you like. If it's useful for you, do it, but then show me the results in a different variant language. We say, okay, we want to insist on background independence because classical GR is background independent. Well, it's background independent with respect to metric backgrounds, geometric backgrounds. There are a lot of background structures in GR. They just happen to be different variant. The space-time dimension is a background structure in GR. The topology normally is a background structure. So you choose a topology, you work with all the geometries on that topology. The signature is a background structure. You don't change it in GR normally. The internal Lorentz symmetry is a background structure. So if you don't, they may all become dynamical as far as we know, which is not much in a more fundamental theory. You may decide that you want to have them dynamical, one or more of them. And we have examples in quantum gravity formalism of one or more of those structures becoming dynamical. And emergent space-time scenarios will be the more radical, the more of these ingredients become emergent. What are general steps to emergence? Well, I'm not so sure if I have to claim full generality, because I'm very aware that I may miss possibilities. I may not have thought of possibilities either already realized in some corner of the literature or in some near or far future. But the steps I'm going to outline, I feel they're pretty general. Whatever is your quantum gravity formalism, it will have to, you can frame it in terms of those steps. Well, first of all, either because you've spoken directly to God, or because you are incredibly clever on your own, or because you're just a fool, you assume you start with some fundamental structure, so an ontology, one you like, one you were used to play with as a kid, whatever it is, you start with that, is your starting point, and your quantum gravity formalism is based on that. In many cases, you don't actually know it. You try to guess. You have a formalist that has a number of consistency conditions and hints of what the structures could be. But if you're speaking of emergence, you tell me the starting point, and you have to show me the end point. So you can postulate it, you can partially derive it by discretizing continuum structures, from quantizing classical entities, from analyzing conceptually notions of geometry, topology, causality, whatever, I don't care. Tell me what they are. The fundamental structure could be more or less closer to GR structures or quantum field theory structures. Again, just tell me what they are. And the same is for the fundamental dynamics. In this, and until the very end of the talk where I will say something about it, I'm going to assume quantum mechanics in some formulation, knowing that it does require, anyway, in a quantum gravity context, and even more in a space-time emergent context, novel interpretation and a different way of using it. And it could be that we will be forced to adopt some generalization of the quantum mechanical framework. But let's assume it, just because we have enough troubles with quantizing gravity and space-time, or with replacing space-time with something else. It's difficult enough that we don't want to take necessarily the issues in the foundations of quantum mechanics together with the others. So, as I said, most steps required to go from the fundamental structures to the emergent spacetime are the same. So let me say what they are. There should be some form of continuum limit. Now, I call it continuum because in many approaches, the new structures are some sort of discrete pre-geometric, proto-geometric structures. So the limit that one has to take can be understood as a sort of a continuum limit. But here you should understand it in a more general sense. It just means that you have to gain control over the collective features and dynamics of whatever are your fundamental structures. Okay? Yeah, and you have to control what changes, what happens when more and more of the fundamental degrees of freedom are required to your physics, are collectively interacting or participating to the result of your calculations. If we have learned anything about quantum interacting many-body systems, which space-time would be under this very broad definition, new quantum structures, there are many, they are interacting, they are not entirely independent one from another. The continuum limit, the collective physics, is not unique. There are many different so-called phases. We live in a world where geometry seems to work as a concept and GR seems to work as a physical theory, so at least one of the continuum phases will be geometric. Geometric meaning it should admit a reconstruction of a spatio-temporal description, approximate. So in this sense, we have some weird quantum many-body system. You study the collective physics. It's a mess. There are many different possibilities for the effective continuum physics. At least one of them should allow the reconstruction of geometry, so it should be geometric. Obviously, your site is fine. I just blurred the picture. All of what I just said is going to be realized approximately. And the need for approximations is constitutive of what we mean by emergence. If there was an exact correspondence, frankly, I would not call it emergence. In the geometry phase, by definition, what I call a geometry phase, it should be possible to have a reconstruction of gravitational dynamics with the typical GR-like ingredients, fields and symmetries and all of that. The dynamics at this point, if the only thing we did was to take some form of continuum collective physics limit of the fundamental theory, may still be fully quantum in principle. If that is the case, then a further approximation will be needed to recover GR as we know it in terms of well-defined values for the observables of the geometry and fields and so on. Now, this is another crucial point that I think we should keep in mind in the context of emergence. There are different types of approximations involved in these scenarios. A continuum, call it, in the generalized sense I mentioned, and a classical one. These are two different things. There are two different things in ordinary physics. So it's even more important we don't conflate them in a definitely not conventional context like quantum gravity and space-time emergence. Classical approximation is one in which, by definition, quantum effects of some sort become negligible. The point is that there's no such thing as the classical limit of a quantum system. There is a classical limit with respect to specific subsets of observables. I give you an example taken from quantum geometry. Suppose you have an area operator, and it's a sum of contributions of individual area operators associated to building blocks, say punctures in a spin network piercing a surface, atoms of space in a group field theory context, whatever, I don't care, not important. It's a sum of different contributions. Quantum states in the theory in which you represent these operators that are semi-classical with respect to the individual contributions will not be semi-classical with respect to the full area. This is a super trivial example for an extensive quantity in a quantum many-body system. So if you take a product of Gaussians with respect to individual contributions, the dispersion with respect to the total thing will scale like the number of punctures. And it doesn't minimize the uncertainty with respect to the global operator. You could have much more, semi-classical states with respect to the global operator. Let alone, of course, taking eigenstates of the constituent. Okay, which raises a bunch of issues with a lot of stuff that is done currently in canonical quantum gravity, loop quantum gravity, and group field theory, and so on. But anyway, the continuum approximation is something else. As I said, is the limit in which you account for an increasing number of degrees of freedom. Is the regime of collective physics. And you can draw a lot of examples, for example, from molecular physics to hydrodynamics. And there is a conceptual difference, but with very practical consequences. The two limits may not commute. So the collective physics may be inherently classical with respect to some macroscopic observable, but it doesn't mean it's classical with respect to the microscopic ones. In the example that was mentioned earlier about the quantum electromagnetic field and the classical one, the classical electromagnetic field is indeed classical with respect to the field. With respect to the photons of the same quantum electromagnetic field, is a highly quantum object, is a coherent state, is a condensate, if you want, of the photons. If you were to take a classical approximation of the photon theory within quantum electrodynamics and then take a collective limit, you will not get the classical electromagnetic field. I'm not sure exactly what you will get because it's quite silly to do it. It will look like a bit of a gas of photons or something like that, but it's something else. And an obvious example is bosons and condensates. If you are to take a classical limit of the atoms before taking the continuum limit, you would miss superfluidity. You will miss all the quantum properties of your fluid, which are there if you just take the collective physics. So there's no reason not to expect the same to hold in a quantum gravity context in which you replace your fundamental degrees of freedom with something else, whose collective physics you have to study. Last step, I emphasized that at the beginning. Yeah, we may recover GR at the classical or quantum level in a redundant description in which you still have diffuse and all of that. But at the end of the day, what we care about is the theory in which we mod out by diffuse and we define localization with respect to physical frames, subsets of degrees of freedom. Now, it's important to stress, I don't mean any of these steps to be sequential, nor individually necessary. These are conceptually different aspects of the issue. Depending on the context, maybe you go directly from here to here, or there is some other combination of limits and approximations. It depends on the system. But the conceptual steps will be of this type. Okay, obviously, if we want to do physics, we are interested in more than just following the steps. In fact, I would argue that the scheme I just outlined and most of the technical challenges and procedures apply equally if your starting structures, non-spatial temporal structures, are understood as physics, so real new entities, or if you just understand them as technical artifacts, regularization tools, some mathematical tool. What I said still applies. However, you will understand this new type of structures that were your starting point as physical only if there is some direct or indirect observational signature of them. Otherwise, okay, sure, you can regularize a theory with some fancy mathematics or a lattice or something else, but if at the end of the day, the existence of that lattice or whatever other mathematical structure disappears, well, there's no claim that something has emerged physically from something else. So what sort of observational signatures? There are many, and this is not a slide about phenomenology, but the point is that we are replacing one or more, and possibly all of them, all of these basic ingredients in our GR, quantum field theory, and so on, with something else. So they're only approximate. With an approximation come corrections. And so those corrections, in principle, are something that could give signatures at the phenomenological level. And by the way, if you are in an emergent space-time scenario, you cannot assume or you cannot expect separation of scales. So the idea that quantum gravity, even in this emergent space-time context, is about the microscopic structure or high-energy physics is entirely misleading. Because the very notion of scale has to do with having some space-time. Okay, so if the whole thing is emergent, is an effective concept, then you may well have at very small distances, very small energies, very low energies or very large distances, some phenomenon which is ultimately of quantum gravity origin. And again, an example would be superfluidity from the point of view of a small perturbation or a fish swimming in the superfluid, apart from the cold. The superfluid is a macroscopic phenomenon, but you only understand it from the point of view knowing that there are bosonic atoms which coherently do something at the quantum level. Okay, now I give you an example. I have no idea at all how long I've taken already and how much time I have left, but I'll pretend I have the whole afternoon. So I give you an example in which I try to illustrate all those various steps and all the different aspects. And this is definitely not textbook material. So the context is called group field theories or tensorial group field theories that were kindly mentioned earlier. So it's a quantum field theory of atoms or building blocks or quanta that are not directly spatiotemporal. They are supposed to constitute space-time collectively. So quantum field theory of this sort of discrete building blocks, not embedded, not living in any pre-existing space-time. So it's a quantum field theory. So I'm skipping, of course, a lot of details because they're not crucial for the main steps I want to highlight. You can have a Hilbert space associated to an individual quantum of the theory, which you can represent as a simplex, a tetrahedron in 3+1. You have or if you come from canonical loop quantum gravity, that's basically a spin network vertex, but treated on its own as if it was a quantum of your system, an atom of your many-body system. You can define geometric operators in the sense of the possible geometry of an individual tetrahedron, but again, without any embedding into a smooth manifold with a smooth geometry or anything like that. There are some intrinsic algebraic data that you reinterpret as characterizing the area of a face, the length of an edge, the volume of the object, and so on. So these are examples of operators. If you have this Hilbert space for a single tetrahedron, you can write down a Fock space for that. You just take tensor products of the Hilbert space for a given number of tetrahedron, and then you sum over all possible numbers. Okay, so we have a quantum many-body system, and these are the atoms. I have assumed bosonic statistics here, and we can discuss what else can be done. Again, if you come or know about loop quantum gravity, is a sort of a second quantized formulation of that, losing a number of the properties and features of canonical loop quantum gravity because we are not quantizing the continuum gravitational field. We don't have an embedding manifold and all things that come with that. Hopefully we also gain something. So you have a Fock space, you have creation and annihilation operators that you can postulate or derive in a number of ways. It will not play much of a role in what I'm saying later, but you can reconstruct extended lattices or gluings of tetrahedra by just entangling these atoms. And maximal entanglement across a subset of degrees of freedom is exactly geometrically realized as gluing two tetrahedra across a triangle. So one can show that there is a fundamental discrete entanglement geometry correspondence. I can say more about this, but again, it's not too crucial for what I'm saying in the following, but potentially it could be. So it's the same type of quantum states as in loop quantum gravity or lattice quantum gravity, but for a number of technical reasons, they're even less spatiotemporal than those you have there. A generic state in this theory will have really no clearly associated topology, no clearly associated standard geometry, except for the properties of the building blocks that I mentioned. There will be wild superpositions. Whatever geometry you try to reconstruct will be, from any macroscopic point of view, fully degenerate or pathological in different ways. And this is even if you forget about quantum superpositions and all of that. So in this sense, they're non-spatiotemporal. Then you associate some dynamics. It's a field theory, so there is some action for the field corresponding to the creation operators, creation annihilation operators acting on the Fock space. There is some partition function, and we can discuss how this could be defined. As a matter of fact, there are different models that one can use. And models are usually defined and introduced for this theory either from a loop spin foam perspective or from a lattice gravity perspective. The guideline being that the interaction processes of these atoms, what in the usual field theory would be Feynman diagrams, should correspond to lattices, four-dimensional lattices. And the amplitudes that you associate to each lattice should take the form, in the appropriate variables, of lattice gravity path integrals. Okay, you write down a model, choose an action such that you expand in Feynman diagrams perturbatively. The diagrams are triangulations, so lattices, simplicial lattices. So you are summing over all possible triangulations constructed by gluing together building blocks, with the amplitudes taking the form of some discretized version of a gravity path integral. Different models, different amplitudes. And then you choose your favorite one, your most promising one. So you have, and when you include matter degrees of freedom, you can add scalar fields in the same sense in which you have a discrete geometry. You are going to have some discretized elements that should concur to form a scalar field in the continuum approximation. Okay, so you have a sum over simplicial topologies and quantum discrete geometries. You want to reconstruct space-time and continuum geometry out of it. Going to be quick. So if you make an hypothesis, a relevant phase, I told you have to find or choose a phase, is a condensate in the same sense as a Bose-Einstein condensate, and technically very similar. And you want to go to an approximation that is the simplest collective one, so hydrodynamics. And there are a number of results in the literature supporting this hypothesis, but of course it remains an hypothesis, not a proof, but it seems to be consistent with what we know. And the mean field hydrodynamics, meaning approximating the full quantum effective action with the classical action, is the simplest one. So you start from that. So it's classical from the point of view of the field here, not from the point of view of the geometries of the lattices, with respect to which it may be highly quantum, in the same sense as the photons and the electromagnetic field I mentioned earlier. So the hypothesis is basically that you treat the universe as a sort of a Bose-Einstein condensate with this as the atomic description. Okay, it turns out that the condensate wave function is a function defined on a domain which is isomorphic to the space of continuum spatial geometries at a point, or mini superspace of homogeneous geometries, like in quantum cosmology, if you know about that. But the equations at this hydrodynamic level are going to be nonlinear for this wave function. It's hydrodynamics. So it's a sort of a nonlinear extension of quantum cosmology that you get in this approximation. A wave function on mini superspace satisfying a nonlinear equation. Okay, and you can expand on how cool this is, but I will not. So you start from this microscopic description, you take this mean field approximation under the assumption of a condensate. You obtain this effective hydrodynamic description, which takes the form of a nonlinear quantum cosmology-like equation. Then you do it for concrete models because you want to go from this general description to, you want to extract the dynamics of observables, that's something that you can compare with GR. So you do it for, it's 5. But then I feel threatened. You do it with a concrete model, aligning with the relational story I was telling you earlier. You need enough degrees of freedom to define localization in time and space. If you're interested in the dynamics of geometry in some effective continuum approximation, you need enough additional degrees of freedom to whatever will become geometry to define points. So you need at least 4 scalar quantities, say, in this discrete lattice gravity initial setup. You need 4 discretized scalar fields, 4 additional numbers so that you can use 1 as a clock and 3 as rods. So you start with a model in which there is all the discrete geometric quantum degrees of freedom. There are the degrees of freedom for 1 clock and 3 rods, and I'll tell you in a second how you use them. And there is some additional matter field. Additional degrees of freedom that you hope will look like a matter field in the continuum approximation, just like you hope the discrete geometry to give rise to a nice generativistic description of space-time. So you start with a model with these degrees of freedom. You can write down the effective hydrodynamic equations for the wave function, for the condensate wave function. Then you work with specific condensate wave function that somehow single out values of 4 of those degrees of freedom so that you can re-express the dynamics as a function of the values of those 4 degrees of freedom, so that it's localized in terms of those 4 values. You make a bunch of simplifying assumptions, you write down the equations. Then you can say, well, I'm interested in 2 types of issues, physical issues, the physics of a background space-time, and you define a homogeneous background by independence with respect to your rods, and perturbations as the simplest approximation to the full dynamics. You do that, so you have background equations and perturbations equations. Then the next task is to go from this general way of writing the hydrodynamic equations into 2 equations for observables. So you take observables, and they are natural observables in a quantum many-body system for which individually you have a notion of geometry, like a notion of volume or a notion of length and so on. For example, you can talk about the total universe volume. Here there should be 3 halves, by the way. So there's a notion of each atom contributes a bit of volume, and then I sum all the contributions at the total volume in my given state. Then you have the total number of particles, of atoms, and a bunch of other observables depending on the degrees of freedom you have in your theory. With the same story of picking on specific values of the 4 scalars you want to treat as clock and rods, you obtain expressions for the number of atoms, the total volume of the universe, the average value of the scalar field, blah, 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 with respect to the given values of the scalar you want to use as a clock. So at a given moment in time defined by the clock. And you can do the same for space. And then you write down the equations for such quantities as expectation values in the given state. This, by the way, apart from the weird interpretation, is exactly what you would do in a Bose-Einstein condensate. And then you obtain, you look at the resulting equations for the observables. You will find that for large enough volumes, the effective equation for the volume of the universe takes the form of the Friedmann equation written with respect to a relational clock given by a massless scalar field. And I'm neglecting the matter contribution here. I can include it. So you obtain what we will say is the classical limit of the theory, but not by taking an h bar going to zero limit. You just consider the collective dynamics, and in a regime of that dynamics, the universe behaves like in classical GR. At earlier times, you find that instead of a singularity of a bounds, at later times, when the interactions of the system become relevant, with less generality, you have to choose, we have analyzed specific models, you find that the interactions of the microscopic building blocks produce at this effective level an accelerated expansion for the volume. And in fact, with some care, you can show that it's a phantom-like accelerated expansion. You can show that the same type of interaction, in fact, can produce early time acceleration with graceful exit. But okay, this becomes a bit more model dependent. You have to check exactly what you're doing with the system. But it shows the possibilities in these emergent space-time scenarios. Okay, and then you can do the same story for perturbations. Given that I only have 3 minutes, I will just skip all the technical details. The statement is simply, you look at the dynamics of the perturbations of your condensate at the mean field level, localized in space through rods, internal degrees of freedom used as rods, and you can obtain an effective scalar field dynamics for your additional matter scalar field or for your volume perturbations. And you can analyze what sort of effective field theory you get for those. Okay, and I'll skip all the technical details. So this is potentially physics, not just a nice or more or less nice conceptual scheme, because there are potentially testable effects having to do with the presence of a bounce that we find this hydrodynamic approximation, with the effective quantum gravity generated early universe acceleration that I mentioned. We can compute corrections due to the physical frame, the fact that you don't have an idealized coordinate frame, but a physical one that you're using, with the emergent cosmological constant and effective dark energy dynamics, all of that. I mean, there are consequences of all this emergent story that if we are good enough, you can make precise, quantitative enough to give observable signatures of the microscopic structures. So you can actually do physics. And even in terms of the effective equations for perturbations, there are many things that seems to be there in our current analysis of the effective field theory for the perturbations. So you can have dissipative terms, you can have effective potential or mass terms for the matter fields generated by the quantum gravity degrees of freedom that you didn't put in at the beginning, and a bunch of other stuff. You can recover. Was somebody moaning or ask? Oh, there was a question. Oh no, sorry. I'll be quick. I'm almost done. You can show that there is a Lorentzian structure with the Lorentz symmetry recover, but it will depend crucially on a number of ingredients. It's not something you can take for granted that you will recover Lorentz symmetry. And you will find a number of possible sources of corrections to standard QFT and GR. Okay, so the only main lesson here is that we have a context where the more radical expectations or fear about general emergent spacetime scenarios can be concretely realized. I mean, so one in which most, if not all, aspects of usual QFT are in fact approximately recovered only in some cases. So unitarity, locality, and so on. Okay, now I have 1 minute. 1 minute for a number of broader issues and things that I think we can learn or at least think about from the concrete examples, but again, as an example of something more general. So I'll mention some of them super quickly, and then I'm happy to discuss each of them more carefully. Okay, these are more directly related to what I've shown. So you get cosmology is an hydrodynamic approximation of the underlying system. Many of the conceptual issues of quantum cosmology seem to be, from this point of view, entirely misplaced. So the very idea of a wave function for the universe comes when you restrict attention to some global observables and you cause grain, and it satisfies not the quantum dynamics, meaning a linear operator acting on the wave function equal to 0, but it satisfies hydrodynamic equations. So the conceptual aspects are very different. The nonlinear aspects with respect to, at the technical level that are different with respect to usual quantum cosmology beyond the conceptual ones are physically relevant. They are the origin of the acceleration in the expansion of the universe that I mentioned. We have seen that cosmological evolution, but also spatial localization are relational. And so they depend on which clock and rods you're using. They potentially are affected by corrections, deviations of these clock and rods with respect to idealized clock and rods. And most principles of QFT and GR are emergent and approximate, as I already stressed. I said that there is a bounce replacing the cosmological singularity. And this seems to be what comes out of the model, and it's quite cool. But I don't believe it. I don't believe it because this was obtained in a very specific approximation. Hydrodynamics, mean field hydrodynamics in a condensate phase. It may be robust, in which case, okay, the theory will convince me that, in fact, we have a bounce. But it may well be that the approximation doesn't hold, fluctuations become much larger. Not only the quantum fluctuations of operators that we already checked, those are fine, but the fluctuations from the entire system close to the regime in which you would have a bounce, and something else happens, the hydrodynamic approximation breaks down. And worse, it could happen that the system undergoes a phase transition out of the geometric phase. In that case, the only thing we can conclude is that in that regime, at the beginning of the universe is not spatio-temporal, cannot be described in a spatio-temporal language, period. It's not that there is a bounce to a contracting phase. Okay, another important point, I mentioned it quickly. Classical GR, but the same is going to be true at the quantum level. You mod out by diffeos, you have to. So what you're left with, formally, in principle, if you are able to do it, is a formulation of classical GR in terms of equivalence classes of metrics and matter fields under diffeos. Nothing is localized. There's no sense in which there is an event in this language. It's diff invariant, but it's it just taking the theory as it is and work out the equivalence classes. We don't do physics like this. We can deparameterize, usually with some less than fully realistic matter fields, but we can do it. So you choose a matter field, you choose a physical frame, and you write everything in terms of that physical frame, and now everything is local with respect to that frame, as defined by that frame. But you can do it with respect to another frame, and another, and another, and another, and I think you got the point. Now, you can do all these deparameterizations. We also know that all of them will correspond to particular gauge fixings of the theory in the limit in which the physical frame is idealized. So it's an approximation that you have to take with respect to the actual deparameterized theory. At this level, we know that we have general covariance or even diff invariance. So nothing will depend on the gauge or the frame. At this level, we have no clue. We simply do not know which aspects of local physics depend on the physical frame we've chosen. And we have no special reason to assume that there's going to be invariance of physical properties. We don't know. Okay, and then I think I should stop, but I wanted to say something about physical laws and interpretation of quantum mechanics, but I can leave it to the discussion later. I have slides. Thank you.